You've most definitely seen SpaceX land its Falcon 9 booster before, and it just seems like magic. But SpaceX most of the time always land those boosters in a small landing pad on the ocean. Why? It seems inconvenient for SpaceX to land in the ocean, then transport the first stages back to shore, and a misalignment could mean the first stage completely misses the landing pad during entry. The short answer: the booster will not survive the trip back to the launch pad. The longer, more in-depth and more fun answer: SpaceX's Falcon 9 has made it almost seem common to land its rockets. SpaceX has flown the same booster 10+ times now, revolutionizing the whole reusable rocket idea. The reason SpaceX lands its boosters in the ocean is that the booster does not have enough fuel to get back to the launch pad. Here's why. The booster's fuel supply is limited. The booster will spend the majority of the fuel accelerating to extreme velocities during liftoff, close to Mach 10, 10 times the speed of sound. By the time stage separation has occurred, the booster just does not have enough fuel and oxygen to return. Also, in orbit, there's nothing to react against. The air is so thin that aerodynamic drag is useless in slowing down the rocket, even if it stopped accelerating. Meaning it needs fuel to actively slow down. Returning to the launch site implies the rocket will have to accelerate to extreme velocities, then after stage separation, decelerate to zero and turn around, which uses fuel, and then accelerate back to high velocities to get back to the launch pad and decelerate back to zero to land. The Falcon 9 Stage 1 booster just cannot do that. It will be inefficient and expensive to use all that fuel, not to mention the extra weight that comes with adding more fuel at the cost of payload carrying capacity. And the physics will not allow it. A worthy thing to note is that sometimes SpaceX does land the booster back at its landing pad on land. Depending on the payload capacity the rocket has to carry, the booster may be able to land back on the landing pad on land. If the payload capacity is small, the booster may have enough fuel to go back to the landing pad on land. If the payload weighs more, the booster will land in the ocean because it won't survive the return trip. And at times, the booster may not even land at all, in the case of super heavy payloads, where all its fuel is being used up just to make it to the stage separation stage. But you may think, does the rocket not launch vertically? Why can't it just fall back in the same vertical path after stage separation? Because the rocket does not take off vertically. Well, it does at first, then tilts horizontally. The rocket's flight path is more horizontal than vertical, because the rocket needs to get to orbit. Rockets in orbit still feel a very significant amount of Earth's gravity, but do not fall to Earth. Well, actually they do. For an object to be in orbit, the object has to move around the globe at such speeds where its horizontal velocity equals the pull of gravity back to Earth. That is, the rocket moves horizontally such that it can counteract that fall to Earth or that pull back to Earth. Its outward radial acceleration equals the inward acceleration of gravity. This creates a sense of zero gravity. The rocket is traveling horizontally at a constant speed, and the gravitational pull attracts the rocket back to the Earth, causing the rocket to travel in a circular path around the Earth. So for a rocket to orbit, it has to move horizontally. All that matters is your horizontal velocity. Your altitude does not matter. Think about it. Imagine being, say, 5 meters off the ground. You could, in theory, maintain an orbit at 5 meters of the ground. That is, if you can go fast enough horizontally to counteract the pull of gravity towards the ground. But that will mean going extremely fast. And at 5 meters off the ground, the atmosphere is the thickest it can be, making it virtually impossible to reach speeds to maintain an orbit. Because moving through thick air at incredible speeds is like moving through honey. It's extremely difficult. This is where altitude comes into play. The higher your altitude, the less difficult it is to travel fast, and the easier it is to maintain an orbit. Also, at high altitudes, the air density is extremely thin, which will cancel out effects like drag and dynamic pressure. So that's basically why a rocket goes up, to get out of the thick part of the atmosphere. For example, for the space station to stay in orbit, it moves around the Earth at 28,000 kilometers per hour or 17,000 miles per hour. So the rocket can't just fall back to the launch pad, because by the time stage separation occurs the rocket has already traveled some significant horizontal distance away from the launch pad, about 100 or so kilometers. So coming back without any fuel is not possible. At stage separation, the boosters are moving at about Mach 10. So SpaceX came up with an ingenious solution. Rather than decelerating the booster to zero then accelerating, why don't they just allow the booster to continue its flight arc path, and only decelerate during landing? But this came with a caveat. Continuing the booster's flight path means the booster might land at some unexpected places, the ocean to be exact. The booster's flight path looks something like this. But why land in the ocean, rather than some other spot on land? These booster landings occur on the ocean because rockets typically lift off at coastal areas. This is because the coast of Cape Canaveral is closer to the equator, which is equally important for rocket launches, for reasons we will not get into for this video. Launching off the coast means the only place the rocket can land is in the water. This means SpaceX would have to provide some sort of accommodation to catch the rockets in the ocean, and then pull the rockets back to the land. But you may have noticed, SpaceX's landing pad, like, "Of course I still love you," is not particularly large. I mean, it is large, but is still not comfortably large enough not to worry about accuracy, meaning any slight misalignments will cause the rocket to miss the landing pad completely. So how does SpaceX maintain such a high degree of accuracy? How does it control the booster to exactly the same position as the landing pad? SpaceX's first stages use nitrogen jets at the side of the boosters, during its time in the vacuum of space, to control its altitude and position. Once the first stage then gets within the atmosphere, it then switches to aerodynamic methods of control, namely the grid fins. These grid fins are aerodynamic surfaces used to control the vehicle's descent very accurately. Grid fins seem to work well on a various range of velocities from hypersonic, supersonic, transonic and subsonic velocities according to Elon Musk. These grid fins help the booster control its orientation, that is, its pitch, yaw and roll orientations, and maintain the highest degree of accuracy possible. Once the ship is fairly close to the landing pad, it then lights 3 of the 9 Merlin engines, to decelerate to basically a hover, and then it turns off 2 of the engines and uses a single engine for precision in the final touchdown. And that's how you catch a rocket from space in the ocean. If you found this video informative, like and subscribe. Thanks for watching and I'll see you in the next one.